What's up, everyone? In today's video, I'm going to be going over Newton's 3 laws, an application of his second law, and then a problem that we'll solve based off the application. So Newton, Isaac Newton, I don't like that N. Isaac Newton has 3 laws called Newton's laws. The first law says if F equals 0, then delta V equals 0. What does this mean? It means if there's no force applied to an object, its velocity will not change. So if there's a rock floating through space and it never hits any other rocks, never comes into contact with anything else, never enters a gravitational field, then it's the magnitude and the direction of its velocity will never change. So whatever speed it was going with is the speed and direction that it will continue going with. Newton's second law says if F is not 0, means there is a force applied to a body, then it's equal to the mass times the acceleration of the body. So a consequence, so if we take this F equals ma, it's one of the most famous equations in physics. If say we apply the first law in the case of the second, 0 equals ma, then either m or a is 0. M is not 0, because if it were, we would be talking about relativistic particles, and then this equation can't be used for them anyway. So that means a is 0, which means that, and remember, a is defined as on average delta v over delta t equals 0. Multiply both sides by delta t, we get delta v equals 0, v final equals v initial, always. So if there's no force acting on a body, it never changes its speed or direction. If there is a force acting on a body, it's equal to the mass of the body times its acceleration. And keep in mind that force and acceleration are both vector quantities. Mass is a scalar quantity. So these have magnitudes and directions. There can be forces acting in different dimensions on an object. They will only affect the acceleration in that same dimension. So if there's a ball, gravity acts only downward on the ball, which means it only accelerates downward. And then Newton's third law is that you may have heard it colloquially, people say things like every action has an equal and opposite reaction. It's if there are 2 bodies, 1 and 2, the force between the force from the first body imparted into the second is equal to the force of the second body imparted back onto the first body in the opposite direction. So if I punch a wall, if I punch this wall, my fist is imparting a force into the wall. If the wall doesn't crack or break, or if my fist does not go through the wall, that means that the wall has applied a sufficient force that's equal to my punching force back into my fist. That's why my fist hurts after I punch something that's rigid. If I do break the wall and my fist goes through the wall, then the wall wasn't able to apply an equal force back in the opposite direction. But in general, this is true. So if there are 2 planets orbiting each other, they both they both have a force of gravitation acting on each other. So the first planet pulls the second planet with a certain force based on their masses and the square of the radius, the square of the distance between them, and it's equal to the force that the second pulls on the first, just in the opposite direction. So these are Newton's 3 laws. By far the most, the one that can be most applied to problems for us to solve is the second law, which I'm going to get into right now. So the best way for me to illustrate the application of this is by just hopping into a simple problem. So let's say there's a 5 kilogram box. 5 kilogram box is pulled up a frictionless inclined plane that is angled at 30 degrees to the horizontal. So 30 degrees with the horizontal, there's an inclined plane, and a 5 kilogram box is pulled up the inclined plane by a rope. It's pulled parallel to the incline by a rope that has a constant force of 40 newtons. And the problem asks us to find the acceleration of the box up the incline. So first thing to do is draw a picture. Remember, this is 30 degrees with respect to the horizontal. Here's a 5 kilogram box, and it's pulled. There's a rope pulling it up the incline. Second thing to do is label our axes, our origin and our axes. Let me call. So you can put the origin wherever you want and define your axes, however you want in physics. Since the box is moving like this, I think I'm gonna make it, instead of having it like X, Y like this, since it's tilted, it'll make everything easier if we tilt the coordinate system. And instead of calling it X and Y, let me call it parallel and perpendicular. Parallel to the inclined slope, and perpendicular for perpendicular to the line of the incline. So instead of X and Y, I'm just calling them parallel and perpendicular. And then let me define upward in the parallel dimension. Upward is positive, down the incline is negative, and I'll define away from the triangle as positive and into the triangle as negative. So having done that, there's our picture of our little scenario. Next, I'm gonna draw what's called a free body diagram, and that is the object in question with all the forces drawn and labeled on the object. So here's our 5 kilogram box, and now we're gonna do some analysis of the forces on the box. Obviously, gravity pulls it straight down, and the force of gravity is equal to mg, where g is the acceleration due to gravity. Meters per second squared. And there is, as we already saw, 40 newtons of force pulling the box up the incline. And then right now, this force is a combination of two. So remember, our axes are like this. So this is a linear combination of its components in the two axes. We can break this up into its respective components, and I'll use dashed lines for components of the force and solid lines for the actual magnitude. There's a component in the parallel direction, and that's equal to mg sine theta. And there's a component in the perpendicular direction that's equal to mg cosine theta. How do I know that this one is cosine and this one is sine? Okay, here's theta. It's our box. Here's the main triangle, and then here will be a secondary triangle made up of the gravitational force and its components in both of our dimensions. So if I move this vector here, you'll see that we have here's theta. This one is theta. Sine is opposite over hypotenuse. Mg sine theta. And then cosine is adjacent over hypotenuse. Mg cosine theta. So that means this one is cosine and this one is sine. And then all we have to do is, oh, actually there's one more force. Since our block is neither burrowing into the inclined plane, nor is it flying off the inclined plane, that must mean that there are two forces in opposite directions equal in magnitude to each other to prevent the box from breaking through the incline, burrowing into the ground, or flying off. It's the same thing if I hold my fist into the wall and apply a force into the wall, it's still not going through the wall, because the wall, from Newton's third law, is applying a sufficient force that's always equal in magnitude in the opposite direction to my fist until I apply too much and the wall breaks, but I'm not that strong. So I'm pushing into the wall with my fist, the wall is pushing back equally. Since there's a component of the weight into the inclined plane, that must mean that there's another force equal in magnitude but opposite direction to this, called the normal force. And it's called that because this force is normal to the surface that the box is resting on. Normal meaning at a 90-degree angle. So here's the surface, and here's the normal force. It forms a 90-degree angle with the surface. So the normal force is equal to the weight of the box, provided that the material that the incline is made of is sufficiently rigid and strong. If it's spongy, it's not gonna work. But if it's wood and this is only 5 kilograms, the normal force is equal to mg cosine theta. So we need to break this Newton's second law, F equals ma, into its component form. F parallel equals ma parallel, and F perpendicular equals ma perpendicular. Let's start with the perpendicular one. So then this is actually the sum of the forces is equal to ma. You'll often see it like this, but really it's a sum. You have to consider all the forces acting in a certain dimension on that body to find the real acceleration. So in the parallel dimension, we have, and remember, up is positive, normal force minus down is negative, sum is you add them together, but minus because mg cosine theta is negative, because that's what we defined early on, minus mg cosine theta equals ma parallel. But yes, ma perpendicular, sorry. But remember what I said, The box is neither burrowing into the ground nor flying off away from the inclined plane, which means that the forces are equal to each other. And because it's not flying or burrowing, the acceleration is zero. Acceleration is zero, the forces are equal. The normal force is equal to mg cosine theta. And then now let's do the parallel dimension. Remember, I defined up the incline to be positive. 40 newtons minus mg sine theta equals ma parallel. Don't confuse this n with this n. This n is a unit of newtons. That's the unit of force. And this n is a force, the normal force. We're solving for a parallel, which is the acceleration up the incline. Let's divide both sides by m. 40 newtons divided by 5 kilograms minus 5 kilograms times 9.8 meters per second squared times sine 30 degrees divided by 5 kilograms is equal to a parallel. 40 divided by 5 is 8. Newtons divided by kilograms is meters per second squared. That's an acceleration. So it's always good to do dimensional analysis. Dimension of newtons, dimensions of kilograms, dimensions of meters per second squared. So if you do newtons divided by kilograms, you should get meters per second squared, which is the unit of acceleration. So that's good because we're looking for an acceleration. 5 divided by 5 is 1. 9.8 times sine 30 degrees. Sine of 30 degrees is 1/2. 9.8 times 1/2 is 4.9 meters per second squared. 8 minus 4.9 is 3.1. 3.1 meters per second squared. The box accelerates up the incline at 3.1 meters per second squared. So what I've shown in this video is I've gone over Newton's 3 laws. I've given an example of an application of Newton's second law and solved the problem of how to do that. This is actually quite a simple problem. The incline was frictionless. Forgot to mention that earlier, but the incline was frictionless. In more complicated problems, there can be air resistance, friction, a bunch of other forces. In the next video, we'll take a look at a more complicated Newton's second law type problem, but this is a very simple one and a general overview of the applications of Newton's second law. Thank you for watching.